Good evening and welcome to GIS 101. This is the video lecture. I'm going to uh, post this online, obviously, because you're watching it online. We will do some activities in class tonight that you should know because you were there. But if not, check it out. I will try to record what we do and make it available, but I'm not promising that that's going to work. But if not, everything that you need should be there. And if you have questions, you can always email me. So let's get started. We're going to talk about Chapter 6 tonight, about using GIS for spatial analysis. So one of the most famous cases of spatial analysis is something that we can actually relate to now. Um, uh, John Snow was trying to figure out how cholera was transmitted in London in the 1850s. And so, in the middle of a cholera epidemic, pandemic, whatever you want to call it, um, he set about to figure out how the disease was being transmitted. And what he did was basic spatial analysis. In other words, he analyzed space as a component in the problem. And what he did is profound and is really one of the earliest examples of doing so. And so in 1854, he looked at cholera and where people died from cholera at in around London, and he began to notify that the deaths occurred in clumps, these clusters. And he wondered, why are so many people dying here? Why are they so close together? These sorts of things. And basically, what he determined was that at various locations throughout London, there was water sources, water pumps, that basically pumped groundwater up for the people. In some cases, these pumps that were pumping up groundwater were really pumping up river water that was flowing through the ground, basically. And in cases where the local sewers ran into the river at the right place, this was being sucked back in to these pumps that were providing water to the people. And so the pumps were in fact becoming infected with cholera, and that's why the people were dying around them. And so when we do spatial analysis, it's always, there's basic questions we ask, like how many, within a distance, and how much, and where at, and that sort of stuff. But you can use simple questions to answer complicated things. And what Snow did here was a really good example. By analyzing the patterns of those infected, he then looked for commonalities. What do all these people have in common? And it turned out to be where they got their drinking water. Now, did that explain every case? Absolutely not. But it explained enough of them to figure out that's how it was being transferred. So one of the things that we can do when we do spatial analysis is we can do queries. And this allows us a means of retrieving information. Now, this turns out to be really important because what we're going to do is pull out subsets of data so that we're not drowned in the volume of data that we have. And we do it a couple of different ways. Basically, when you run a query, use something like SQL, which is a structured query language, to define a set of criteria, and then it extracts all the information from the database that meets that criteria. And you can do other things. You can ask binary sort of questions like 1, 0, yes, no, real basic things. You can do spatial queries where you look at stuff like find everything that is within a distance of this place, or everything that's within the confines of this area. You can also buffer things. So, for example, you might, if you were in Jon Snow time, you might put a buffer out to a certain distance around every well, and then you could count the number of people who died within that area. You can also dissolve. Dissolve is actually pretty useful. I've used that on some stuff I'm going to show you later, where you can aggregate information by one field. So you can dissolve by one field. For example, say you have all the county information in the nation, but what you really wanted was all the information by states. Well, you could take the county information, and somewhere in that county information it tells you what state the county's in. You could dissolve by the state field, and if the value was the number of coronavirus cases or something, you could then have it to sum those cases per state. So it'll take this county data with all this information, aggregate it at the state level, and then add up the fields that you want. So really interesting tools and really powerful ways of taking information and generating knowledge. That is at the heart of what we do in GIS. Information is useless, okay? Information is just facts and figures, numbers, dots on a map. Without context, information is simply information. It's no more useful than trying to read the Encyclopedia Britannica backwards, upside down. There's no sense to what you're seeing, to what you're reading. The letters don't make sense. The words aren't in the right order. The letters are all misshapen. Okay? That's information. Knowledge is when you take information and you examine it and you analyze it and you use it to generate new understanding. And so it's like taking that encyclopedia and turning it around and reading it in the right direction. And now all of a sudden you've got actual knowledge, facts, information about something that is understandable. And that's where it really matters. So here's a good example from the textbook. We have this road going east to west. I think it's probably Route 66. Or maybe it's Route 70. I don't know. Anyway, for example, if you were tracking a serial killer and your idea of his MO was that this particular person was a long haul trucker and that they traveled east to west across the country on a certain route. And so you would imagine that all their victims are probably going to be from an area within a distance of that road. And so you could create a buffer along that and then plot all the missing persons data around the nation, and then spatially select all the ones that fall within the buffer zone, and that would give you a smaller group of missing people to compare to your potential serial killer to try to figure out who victims might be. Here's a nice example of county data for, I believe this is Ohio. And you can see each of the counties, but what if you don't want the counties? What if you want Ohio? Well, I talked about dissolving. If you dissolve based on the state field, you would get that, the polygon of Ohio. Within a buffer, you can select spatially. Here we're selecting all these cities that fall within a certain distance of a highway. The other thing that we can do that's really, really useful and really, really powerful, and something that you'll learn more about, and in a demonstration tonight in class, we'll see how you can do a little bit of this, but I want to talk about this idea of an overlay. Okay? An overlay is basically when you stack one piece of digital information on top of another. And we do this all the time. And at a low level of analysis, what we do is we create these visual interpretations, and then we make the knowledge from that information. Okay? When we do it in a more advanced structure, what we do is we create a model that will take that two data sets and create a third output that's not just a simple overlay, but has the analysis built in. So it gives us a metric to identify a result, to choose between locations, to identify places that meet criteria, not just to visually look at it and say, oh yeah, this place here has got that and this. So when we do overlay functions, there's some things that we can do, like I said, other than just putting them together. And some of these are basic functions like intersect and identity and symmetrical difference and union. So let's look at intersect. With intersect, we have two data sets. And basically, when we use an intersect function, it's going to find data that is common to both data sets. Okay? In other words, to be in your final output, that piece of space has to exist in both the blue squares and the red circles. Now, if you were to lay the blue squares over top of the red circles, the only space that's common to both would be what you see for the intersect, which is those tiny little pie slice shaped objects. Now, if we did identity, identity would join the two data sets together, but it would do it differently. So we're starting out with the blue squares, and then we're going to overlay the red circles with an identity function, and what it's going to do is then tell us what part of the blue squares is in the red circles. Excuse me. Another one is symmetrical difference. Again, blue squares, red circles, add them together. In this case, it keeps data that's in both data sets and removes any information that is common to both. So basically, it's the inverse of the intersect function. And then lastly, we have the union function, and unions are really, really common. We take the blue squares and the red circles, and it simply combines those together. Now, the interesting thing is the lines. Where an object is in both the blue and the red, it has its own shape. Where it's just in the blue, it has its own shape. Where it's just in the red, it has its own shape. And what this does is this sort of enforces something called a one-to-one cardinality, which turns out to be really useful for doing analysis because it allows you to join data without summarizing it. So let's look at some other sort of basic spatial analysis stuff. For example, if we looked at the image on the left and we were looking for places that had trees, and if it has trees, it's going to get a value of a 1. So you got 4 cells on the left, and so the top left, the top right, and the bottom right all have trees. Okay. What if we're looking for water? Top left, or top right, bottom right. And that's what would be on the bottom. So it's a simple, you oppose a 1 or 0, a binary question, to your data. Of course, in this example, we're going to use these photos. And so you establish a criteria, is there trees? If you see trees, it's a 1. If you don't see trees, it's a 0. Is there water? If you see water, it's a 1. If you don't see water, it's a 0. Binary choices, yes, no, true, false, 1s, 0s. Now, what if we took those different data sets, the tree one, 1, 1, 0, 1, and the water one, 0, 1, 0, 1, and we multiplied them together? The 0 layers in your binary structure multiply out to a 0 no matter what's in the other data set. So if we multiply those two data sets together in an overlay function, we end up with identifying only places that are trees and water. Has to have both, doesn't make it. What if we add them together? Well, if we add them together, we get something different. We get interpretive numbers. So when we add them together, we get a 1, a 2, a 2, and a 0. So what does that mean? Well, if you have a value of 1, it means you have either trees or water. If you have a value of 2, you have trees and water. And if you have a value of 0, you have neither trees nor water. Simply by thinking about what the 1 and the 0 represents in both of the data sets, you can see how you can combine these things and how the math functions allow you to dictate what the outcome will be. This is the beginning of understanding how you can create complicated models using simple, basic types of questions. Some more examples of spatial analysis. Here we have all the cities in Ohio, and we've created something called a distance raster. A distance raster is super useful. What it does is it creates a raster surface for your study area, and any place on that study area that you were to select, it will tell you the exact distance to the closest city in Ohio. Not what city, but simply how far it is to a city. Now, they've classified it. Sorry for the yawning. It just happens when I make these videos. We've created these distances and classified them out using some sort of technique. There's a bunch of ways to do that. I'm not going to go into that today. But you can see, like in the bottom right-hand corner of that image there on the top left, that's the place that's really a long distance to any of the cities. And depending on where you're at in that corner and which direction you move, you can get closer to some cities than others. And there are places where you can go where you can, still be a long ways off. Now on the right, they've scaled this to 10 different ranges instead of these different classes. Very similar kind of a setup. Basically what it does differently though is it just divides it into 10 groups and sets it like that. So I talked a little bit about modeling earlier, and so I want to talk about this idea of a suitability index. A suitability model or an index model is the most utilitarian and most basic of the more advanced, more useful models. It's not as simple as a simple Boolean model with ones and zeros, but they're not super complicated. For example, if you're trying to build a landfill, you might want to be in the forest, away from the rivers, but near a road. And so based on these criteria, you could rank out each of your data sets and standardize them and do all the stuff that you have to do in a model. And then this example here, they're simply adding them together. The basic idea in an index model is you get a score. It's called an index score. An index score means absolutely nothing. Okay? An index value of 13 has no significant meaning. It simply means it's greater than a 12 and it's not as large as a 14. So if you construct your model so that distance to forest, the longer the distance, the better. Distance to river, the longer the distance, the better. Distance to road, the longer the distance, the better. Then the bigger the number, the better the location. It doesn't say, well, this is really far from a forest and really far from a road, but it's really close to a river. It doesn't weigh anything any differently because these are all weighed equally in this model. It simply gives you a numerical value that says, of all the potential locations, those top two cells on the left and the top middle, that's your three best locations to do whatever this model is for. When we begin to think about the complexity that we can have with spatial analysis, it's literally limited to your imagination. And here, for example, we just look at all the different data layers that we could combine together for modeling purposes, for database purposes, for various dashboards and front-facing architecture within a county or a city or a state. You might have administrative areas, you might have addresses and any kind of regulated uses or restrictions. You could have separated rights and encumbrances, basically who owns what. You could have ownership and taxes, parcel information, corners and boundaries, a survey network, and aerial photos and hydrology, and all these different data sets could all be combined together to model any number of things. Here we have some examples looking at urban development going from 1980 to 1995 to 2020 to what it's expected to be in 2040. So if you just look at this, this is what Southeast Michigan Council government, so this is looking at something in Michigan along one of the Great Lakes, probably Lake Michigan, don't you guess? And you can see how they've shown the growth of the urban area over time. How would you come up with this? Well, a lot of different ways. The best way here is something called land cover or land use. And basically it's some combination of techniques, usually remote sensing, that develops some sort of an algorithm that allows it to, on a pixel by pixel basis, determine what is the current use of this land at this location. And you make classes, and then things have to fit in a class. And so it may not be a perfect fit, but it tries to find the class that it's most like. And so the three options here we're dealing with is urban, agriculture, and forest. And so things tend to want to fit in one of these categories. And over time you can see how the amount of urban has increased. The amount of forest has decreased some, and the agriculture has decreased some. We also use GIS and spatial data for a lot of stuff. Here we have a dispatch layer. In 911 setups, phone calls come in, somebody needs help, they give you an address, or the phone call itself produces an address. That address goes into a dispatch management system like this. And the moment that happens, it does something called geocoding, where it converts the address into a point location, shows you where it's at spatially, allows you to identify the closest resources, EMS, fire, police, what have you, and then it routes the fastest route from there to the location, sending that out to the fire or the EMS services or police or whatever it is that's with the call. And all this is contingent on the GPS satellites, the geospatial information, GIS programs, and basic spatial analysis that does things like routes the path, geocodes the addresses, that kind of stuff. So I wanted to share a little bit of stuff that I did, some spatial analysis I did on my free time over the weekend because I was just, well, I was a little bit bored and a little bit concerned. And I really got tired of people on social media talking like this potential pandemic wasn't really an issue or was going to be the end of days, if you will. And so I knew that in reality it's somewhere in between. And so I wanted to try to put numbers to it. And spatial analysis is just a means of taking, like I said earlier, information that without context doesn't mean much and generating into the knowledge to understanding. So what I did was I found, and I always like doing research on my home state because I've already got all the data downloaded. What I did was I identified every hospital in the state, okay? And then I downloaded census tract level population data. Now, we know that the biggest at-risk groups for the COVID-19 virus is people over 65 or with compromised immune systems, and the people over 80, some are really at risk. But I just decided that I would pick a level, and the level I picked was 65 and older. And while at 80 some and older, the rates are closer to, like, you know, much higher percentages, and at 65 in a lot of cases it's down closer to 1. I went with a number of about 2% and used that age. Okay. I then did something interesting. I spatially joined the data from the hospitals with the census tracts. And basically what I did was I identified the closest hospital to every census tract. Then I dissolved those census tracts. And so each of these polygons you see across the state represents a service area for a hospital. And because I dissolved those census information with it, I had it to sum up the total number of people over the age of 65 within that new polygon. Okay? And then I simply multiplied that by 2%. And the numbers you see on this map represent what I call the potential death toll. And so for these regional hospitals, if everyone were to become infected, and that's the key, everyone, 100% infection, which, God help us, we're not going to get there. It should be much, much lower than that. But if it was, at my local hospital here where I'm from, 133 people would likely not make it. Now, I don't even begin to want to know what that would look like for this hospital, because this hospital only has 25 beds. Okay? And there is a potential there for 133 fatalities over the course of the disease with 100% infection. So I begin to wonder what else we might look at. And so, well, what if I broke it down instead of by hospitals? What if I did it by county? And so I looked at all the 55 counties in West Virginia, did the same kind of calculations, the same things, assuming 100% infection and assuming 2% mortality, and this is what it amounts to. In the county I'm from, Pendleton, that's 34 people. Now, you might say, well, that's not, super horrible. This is a very small county in terms of population, and that's a lot. Other counties will not fare as well. Berkeley, 237, that's around Martinsburg, if you're familiar with that area. Down near the state capital, in Kanawha County, you're looking at around 650. Some of the counties over along the Ohio River, anywhere from 1 to 300. Some of those small little counties up in the far north, in what we affectionately refer to as Pennsyltucky, you're looking at hundreds of people in counties that are really, really small. Even having said that, people still don't really understand the risk. And so I looked at the total number that we're expecting, and I divided that out by the size of the county and figured out how many square miles per fatality. And then I said, okay, well, what is the radius of a circle that size? And basically what that ends up with is you just take an average place and say, okay, if I go out to this distance, the likelihood is that somebody inside that distance is going to succumb to this. And in my home county, that means that within a 15-mile radius of where I'm at, or where anybody's at, you can expect to see someone pass away from this disease. Assuming 100% infection, 2% mortality of people above 65. These numbers change quite a bit, and it's kind of a telling number. If you remember, we looked at the number of cases in some of those counties where, like up around Wheeling, up in the top of the northern panhandle, that distance is like 5 miles. Other places, down in the state capital, it's at 17. It's a slightly larger area than Pendleton, where I'm from. And so it's a little bit bigger circle, but it's still the same basic premise. Now, I don't begin to know, I'm not an epidemiologist, I don't know what the infection rate is going to be, what the social distancing effect will have on it, but I know this, it's going to decrease it. So when we look at these numbers, initially my hospital area here locally was looking at 133. If we were to cut that infection rate just from social distancing from 100% down to 50%, then instead of 133, you're looking at about 65 or so, 66. That's a better number. What if we got the infection rate down to 25%? Cut it in half again. Then we're down into the 30s. And what if we got that from 25 down to 12? You're looking at like 15%, 15 people. What if we could get that down into the single digits? What if we get that down to, 8, 10%? We might get it down to a situation where we only lose 4 or 5 people. And that is the point behind the social distancing. If we can limit the spread, we can limit the carnage, the damage. And more importantly, this disease can run its course. And by run its course, I mean one person infects 10 people, those 10 people infect 10 people each, and so you see how it multiplies exponentially. If we don't make contact with one another, if we stay separated by some distance, we can end up in a situation where instead of doing that, people get infected, people get better, and they don't infect more people. And so fewer people become infected, and eventually, if a small enough number of people are infected, it'll just die itself out. All right, I think that's the last slide I've got for you. No, maybe some more. Oh yes. So, no matter how serious the situation, I can't help myself. With all the jokes and everything going on about toilet paper consumption, I decided to calculate up the number of rolls of toilet paper that people would be using on a monthly basis by county. And then it's usually just normal everyday numbers from the various toilet paper industry standards is how many rolls per month a person uses, multiply that by the total population. In my county, to get through a month, we need 15,134 rolls of toilet paper. Other counties need significantly more. I then mapped this out. I used a basic three-level classification scheme where the counties with the lowest numbers are all in one, the ones with the middle are the next, and then the ones that have the most population obviously have the darker ones. And so I broke it down as low-level, mid-level, and big-time wipers, just, because I could. Then it got me thinking, I shouldn't be making fun of stuff like this. I should actually try to do things useful. And so they're recommending we wash our hands 10 times, or not 10 times a day. They're recommending we wash our hands for like 20 seconds. So I did some research, and they talk about brushing your teeth and how long you brush your teeth and how much water you can save by turning the faucet off when you brush your teeth, etc. And if you break down the volumes that they tell you, essentially the 20 seconds that they're telling you to wash your hands with your faucet wide open, we use about 2 liters of water. Okay? So I said, well, what if we're in and out doing a lot of things and we end up washing our hands like 10 times a day? Based on the population, how much water are we going to use? And so I ran those numbers around across the state, and you can see in the county I'm from, Pendleton, that's 40,000 gallons of water that we're going to use to do that. And so I called those low-level Larrys. The light blue, the next level up, these are counties that have a slightly larger population. I call them Splashy Sallies. And then the next level up is the mid-range Mikes, and the next are the deep well eaters because they're going to need some water. And then the dark blue are the ones where they use the most water. And down near the state capitol, you're looking at, let's see, a little over 1 million gallons. Million gallons. Wrap your head around that. And so I put that down as that's the level where I hope their water comes from a river, because it's going to be a problem otherwise.